This is part 2 of lecture 13. In this part, we mainly focus on the Salin and key filters. We'll see how we can derive the transfer function for these second order Salin and key filter circuits. What are the cutoff frequencies and how we can construct higher order filter circuits using the Salin and key filters. So now we'll discuss what is the transfer function for this second order Salin and key filter circuit and how we can uh, derive that. The deriving of the transfer function for the second order Salin and key filter is not that straightforward as it is for the first order filter, because here we have more circuit components and it will need a little bit of analysis, circuit analysis. However, we will not show all the details of the circuit analysis, because that is just pure circuit analysis and has nothing to do with electronics, and I am pretty sure you will all be able to do that, because that's what you learn in circuit 1, circuit 2 courses. You can do it in many different ways. You can use the nodal analysis or any other technique. So here what I will do, I will show you how we can solve that and determine to derive the transfer function for this second order filter circuit using the nodal analysis technique. So first one, what we need to do, we assign the two nodes, we identify two nodes and they assign the node voltages. One is this node here, we assign node voltage Vx, and another we identify another node here at this point, and we assign a node voltage V plus, that is the voltage at the non-inverting input terminal. And the other two nodes we have here at the input is Vi and output is V0, that are already assigned, so we don't have to do anything. So we just assign the two voltages at these two nodes. So that is our first step, identify and assign node voltages Vx and V plus to the two nodes. And next we have to write the node equations. Now write the node equations at the two nodes, and I'm pretty sure you are all expert on this. Of course you do know how to write the node equations, and it will be easy for you to write the node equations if you show first the currents, how the currents are flowing. Let's say current here is I, the input current, and then there are two branches, so this input current will be split into two branch currents. Let's say this is current I1 and the current that is flowing in this branch is I2, so that is how this current will be split. Now this one goes this way, this is again, there are two paths, but as you know, the current into the input of the ideal op-amp 0, so we expect that all of this current I1 will flow through the capacitor C1, so it will look like this. The same current I1 flows through the C1, and since the current here is 0, so from this we can write the following current relations, that I1 is summation of I1 plus I2, and the same current I1 flows through both R1 and C1. So these relations will help you to write the node equations more accurately without making any mistake. Now also there are some voltage relations here. You see that because of the virtual short circuit condition that applies to an ideal op-amp, we are assuming the op-amp to be ideal. V plus will be same as V minus, so these two voltages will be same. And since, see, this node, this terminal, the negative inverting input terminal is connected or shorted to the output terminal, so V minus will be same as V naught. So we can write that V plus is same as V minus, which is same as V naught. So that means V plus voltage at the inverting input terminal, voltage at the non-inverting input terminal actually is same as the output voltage V naught. So you can, once you have written the node equations, you can replace V plus by V naught, right? So this is how we can get rid of this voltage V. You can get rid of this voltage voltage V plus, and you will have V naught in the equation. And the other, then you have two node equations. Because of the two nodes, you have two node equations. Solving these two node equations, you can get rid of V plus Vx, this node voltage, and you'll be left with only Vi and V naught in the equations. So next, what you do, you substitute S for J. You have J omega in the equations because of the capacitor, the impedance of the capacitor 1 over J omega C1, 1 over J omega C2. So you replace those J omega by S. Now you solve for the transfer function, which is ratio of V naught by Vi. So once you have done that, then you have got your transfer function. This is how you can follow. If you follow these steps, you can get the transfer function for the second order filter circuit. Now let's say we have followed all the steps as is outlined here, and we have derived the expression for the transfer function. Now what is our final for the transfer function for the second order low pass filter, second order silent and key low pass filter? So finally the expression will look like this. You see, looks very different. We have completely different terminologies, different notations, and only S is known. S is J omega. So what is omega naught and what is Q? So omega naught is given by this expression, which is basically is the cutoff frequency for the filter circuit. As you remember, if you remember, the cutoff frequency for the first order filter circuit is 1 over RC, and this is a second order filter circuit. We have two R's and two C's, and cutoff frequency takes this form 1 over square root of R1, R2, C1, C2. So that is the our cutoff frequency omega naught, and then the Q is a constant which is given by this expression. So it depends on the circuit parameters, values of the resistor and the capacitor. So after solving for the node equations, you derive the expression for the transfer function V naught by Vi, and after some manipulation of that transfer function, you can write the transfer function in this form, where omega naught is this and Q is this, and this is what is known as the standard form of transfer function for the second order low pass filter. Previously we have shown you the standard form of transfer function for the first order filter, and this is the standard form of transfer function for the second order filter. This is specifically for the second order low pass filter. So for S0, if you put S0, you see that magnitude will become 1. So at 0 frequency or very low frequency, you have maximum transmission, 100%, almost 100% transmission, and at very high frequency, as S increases, transmission will drop. It will keep going down, and at very high frequency it will approach 0. So in the last slide we showed you the transfer function for the second order low pass filter. Now we'll show the transfer function for the second order high pass filter. So we have the second order silent and key high pass filter. If you follow these steps that we discussed in our earlier slide to derive the transfer function, then you can get this expression for the transfer function for the high pass filter as as we have seen that for the low pass filter, the transfer function, here we have omega naught square. The only difference for the high pass is that we have s square instead of omega naught square, and the denominator is the same as that we had for the low pass filter. So instead of omega naught, here we have s. So s is our frequency, so in frequency is 0, you see that, and the transmission is also 0. That is what we expect for the high pass filter. At low frequency the transmission will be low, or 0 frequency it should be 0, and that is what we get. The lower is s, the lower will be the transmission. The higher is at very high frequency, transmission will approach 1. So that is exactly matches with the characteristics of the high pass filter. Now here omega naught is the same, the cutoff frequency that we have for the low pass. So for low pass, high pass, the expression for cutoff frequency is same as we have seen also for first order filter. Both the high pass and the low pass, they have the same expression for the cutoff frequency, and that is also true for the second order filter. The other sorry the other is the constant, that is q here in this expression. So the q is given by this expression. Now this is slightly different from what we had for the low pass. So q is different for the high pass and the low pass filters. For the low pass, here we had 1 over r1 plus 1 over r2, and here we had 1 over c1 or c2. So this part is different. Otherwise the cutoff frequency is same, transfer function almost same, the denominator is same, only numerator is different. Numerator, here we have s squared for the high pass, and for the low pass you will have omega naught square. So these are some uh, subtle differences between the transfer function between high pass and the low pass second order filters, and the subtle difference in the quantity q between these two filters. So that you need to remember those small differences, and yeah, that's it for the Sallen and Key filters. So now we'll see how we construct the higher order filter circuits using the Sallen and Key filters. So how we can construct, we have seen in our, at the beginning we have showed you how we can realize higher order filter circuits by joining the first order filter circuits. Now we'll see how we can get higher order filter circuits using the Sallen and Key filters. So if we join a first order filter circuit with the second order Sallen and Key filter, low pass filter, then we'll get a third order low pass filter. Now if you want a fourth order low pass filter, what we do, we join two second order filter circuits in series and we get a fourth order low pass filter. So two Sallen and Key low pass filters are joined in series and we get a fourth order low pass filter. Now if we add another first order low pass filter with this fourth order low pass filter, then you get a fifth order low pass filter. So we have two second order low pass filters and then another first order low pass filter, and overall it will be a fifth order low pass filter. So this is how you can construct any order of filter circuit that you want. Now finally we show a band stop filter circuit, how we can construct a higher order band stop filter. So here we are showing a third order band stop filter. So at the top we have a third order low pass filter. So this is a second order Sallen and Key low pass filter that is connected with the first order low pass filter. So together they give a third order low pass filter. And in the bottom here we have a second order Sallen and Key high pass filter that is connected with a first order high pass filter, giving us a third order high pass filter. So and now output from these two are connected to the input of this adder circuit, and we have a common input Vi. So altogether they realize a third order band pass filter, band stop filter. So the in the top, these two will realize a third order low pass filter giving a fall of gain of 60 decibel per decade at low frequency end, and these two together will realize a high order third order low pass, third order high pass filter giving a fall of gain of 60 decibel per decade at high frequency end. So both at low frequency and at high frequency end will get a fall of gain of 60 decibel per decade, and that is what is needed for a third order filter circuit, and that is how the third order filter circuit is defined. So altogether we'll get a third order band stop filtered circuit, and hopefully you will be able to construct any order of filter circuits with a low pass, high pass, band pass and band stop. Thank you.